Welcome to lesson 36, solving 2 by 2 systems by substitution method. This is a very nice method, and unlike the graphing method that we were just looking at in the previous lesson, this gives you exact solutions. You never have to worry about squinting to try to read the solution precisely. These will give you exact solutions. Before I start, I want to point out, if you go down to the description of this video, look underneath here, and you'll probably have to hit the see more button or the whatever to actually see at all, but I will put a link to this particular sheet that you're looking at here that I'm about to take the notes on, so that you can print it out if you like and take your notes on it. And I'll also put a link to the homework that goes with it while I'm at it. Okay, so without any further ado, let's get started on here. So some systems are just going to beg you to use this method, and this is a perfect example of one. See that bottom equation where it says y equals, and I don't even care what it equals, it's just y equals a whole bunch of stuff. When you have this form, this is begging you to use the substitution method. So what is the substitution method? Well, y is equal to 3x minus 4. That's what the bottom equation says. Y is the same thing as 3x minus 4. Well, that means you can come up to the top equation, and where you see that y there, 5y, you can replace it with 3x minus 4, because they're supposed to be the same thing. That's what the second equation says. Second equation says y is the same thing as 3x minus 4. So I have 2x plus 5y, but wait, y is the same thing as 3x minus 4. So I'm substituting, just like tag team wrestling. I'm just substituting it in, hence the name of the method. Why is this a good method? Well, look what happened. Look at this equation here. This equation has only x. It doesn't have y. It has only x. And so that means we're going to be able to solve this thing. So you remember playing with equations like this, right? So you do the old distribute, 5 times 3x is 15x, and then you do the old 5 times negative 4 is negative 20, and then that equals 8, right? You want to combine your two x terms together. These are both on the same side of the equation, so they just add together. 2x, 15x is 17x. And then this minus 20, you don't want that there. You want that on the other side of the equation. So you do the old add 20 to both sides trick, so that here it'll cancel off, and on the right side you'll have 28. So I'm assuming you've seen this before, and I can go rather quickly. Last thing to do is you have to divide off the coefficient of 17 from the 17x. You don't want the 17, you just want x. So you divide both sides by 17, and here's your answer, for x anyway. X equals 28/17. Perfect! A nice exact answer. I defy you to read 28/17 by looking at a graph and going, oh yeah, that's where that is. That's x equals 28/17. Yeah, I can tell. No, you can't. So that's a big advantage of the substitution method, is it gives you exact answers. And it didn't even take that long, really. Except we're not quite done. We still have to find y. Remember to get y. So all you got to do to get y is plug this answer into, and it really doesn't matter which equation you use. You could plug it into the top equation. Remember, the solution to the system is supposed to be the point that satisfies both equations. So if it satisfies both equations, you should be able to use either equation, right? I'm going to use the bottom equation, though, because the bottom equation is already kind of solved for y. Y equals 3x minus 4. Well, wait. Same thing. X is the same as a 28/17, though, right? And then minus 4. So I'm substituting again. So we got to work this out. Now remember, when you're multiplying fractions, you think of that 3 as a 3/1. Okay? And now you should also think of that 4 as a 4/1. Why is it important to do that? Because we're playing with fractions here. And if you're playing with fractions, you want everything to look like a fraction. And so 4 doesn't look like a fraction, so you put it over 1. You remember that's legal, right? And then since we're looking at common denominator of 17 here, I need to make this, have a common denominator of 17. So you have to do the old multiply by 17/17 trick. So continuing, y equals. Now here, remember how you multiply. You multiply straight across, top and bottom. Don't get fancy. Straight across, top and bottom. The one thing I could try to do first is cross cancel, but does 3 go into 17? 3 does not go into 17, so I'm not going to be able to cross cancel. So continuing, straight across, 3 times 28. That would be 3 times 20 plus 3 times 8. So that would be 60 plus 24. That's an 84/17 minus. And then here I got 4 times 17 is 68/17. And so what I'm getting for y is, I'll tuck it underneath this one, 84 take away 68. What is that, 16? Am I doing that right? 68, 78, 84, yep. And so there's your solution. These two things together, x is 28/17, y is 16/17. Cool, I hope you like the method. I like it, it's a cool method. Like I say, there's certain equations that'll beg you to do this. Here's another one begging you to do this, because if you look at that bottom equation, it has the form x equals stuff. So if I scroll back up, this one had the form y equals stuff, and that was just begging us to substitute. This has the form x equals stuff, and again, that's begging us to substitute. So x is the same as a 4 minus y, which means that this x has to be the same as a 4 minus y. So I'll just substitute it right in there. 3 times x. Wait, x is the same as 4 minus y. There we go. And then we add the y, and then we get the 4. And then you look at this equation and you say, there's only one variable. There's just a y. I think I'll solve it. So 3 times 4 is 12, minus a 3y. Then you get this plus y equals a 4. These are on the same side of the equation. You just combine them together. They're like terms. Negative 3y plus y is a negative 2y. So technically, just bring the 12 down, bring the 4 down. And then this is the part where you say, I don't want 12 over here. I have to subtract that. Right? So you subtract the 12 on both sides. Don't forget that this is a negative 2y. 4 take away 12 is a negative 8. And then your last step would be to divide by the coefficient, which is negative 2. Divide by the negative and everything. You want the negative to cancel. You want the 2's to cancel. Y equals negative divided by negative is positive. 8 divided by 2 is a 4. So y is equal to 4. Woohoo! Remember, that's only half our answer. So let's go get x now. So what I'll do now is I'll combine this and this. The bottom equation says x equals 4 minus y. But we have y equals 4. So that tells me that, well, x is equal to 0. And so the solution to this set of equations is x equals 0, y equals 4. Now, if you wanted to check your answer, in fact, let's check in a nice color. If you wanted to check your answer, the exact way is to try the solution in, and this is the important part, both of your original equations. You have to do both. So I would come up to here and I would say 3 times, let's see, we're saying x is 0, okay, plus y, but we're saying y is 4, okay. Does that equal 4? And if you look at that, that's true. The bottom equation says x equals, well, x, we got 0 for x. Does that equal 4 minus, and y is 4? It does, right? It checks. So that's the exact way to check it. Now, this particular system of equations wasn't hard to check exactly, but sometimes you get weird fractiony, decimally answers, and you want to be able to check, and you don't want to have to get all involved. So a nice, quick and dirty is to bang out a nice, quick graph, because it doesn't take too long to bang out a rough graph. So roughly speaking, well, maybe I'll just kind of put these in slope-intercept form, because that doesn't look too hard to do either. That would be y equals negative 3x plus 4, and this would be y equals negative x plus 4. I've just move terms around so that they're in slope-intercept form. So the top equation, I had to subtract 3x from both sides, basically. The bottom equation, I added y on both sides, and then I subtracted x on both sides. So anyway, this top equation, call it equation 1, y-intercept of 4, slope of down 3 over 1, negative 3, down 3 over 1, down 3 over 1. Okay, so this line's doing something like that. And then this other one, negative x plus 4. Oh, didn't even have to graph it really. It goes through the same y-intercept, and it's got a slope of negative 1, so it'll be down 1 over 1, and so on. So anyway, you can see where these two lines cross. They cross right on the y-axis. Right on the y-axis at y equals 4, hence the solution checks. Now, graphing is not going to show you that your answer is exactly right, but it's a nice way to show, yeah, that's about where it is. Like if you graphed these lines and you found out that they were intersecting over here in the third quadrant for some reason, you'd say, well, wait a minute, it can't be intercepting up here at y equals 4, x equals 0, y equals 4, so I did something wrong somewhere. Either I'm graphing this wrong, maybe I should check my graph, or anyway, it's a nice way to get a nice second opinion, so to speak. It's a nice way to get a second opinion is with the quick and dirty graph. So I believe if we go to page 2, I believe I have another example which is kind of the same thing. Look, they're both equations are begging us to use substitution because one says y equals stuff, the other says y equals stuff. So yeah, go ahead and try this one yourself. Get a little practice going there. Solve this. I think I'm gonna, well, it doesn't really matter how you do it. I'm assuming you've paused. Now I'm assuming you've unpaused. Okay, y is equal to negative x minus 8. Y is equal to negative 5x plus 6. Y is equal to this. Y is equal to that. This must equal that. Okay. Of course, you could do the same thing by saying, ooh, how would I do that? I would do it this way. I would say, oh, I'll take this and I'll substitute it into there. Right. Same thing. Anyway, you end up with a not bad looking equation. Now this negative 5x is on the wrong side of the equation, so let's do this. So I got a 4x minus 8 over here. I got a 6 over here. Well, that 8's on the wrong side of the equation. It's still on the wrong side of the equation until I add 8 on both sides. Then I've got 4x equals 14. Dividing both sides by 4 and dividing by 2 to simplify. Always reduce your fractions, please, please, please. You got x equals 3.5. 7 halves or 3.5. Okay, that's not bad. Just make sure you get y. You can use either equation, it doesn't matter which one. I might as well use the top equation, it looks a little simpler. Negative x minus 8. So negative, stick my solution for x in, 7 halves, minus 8. So that's a negative 7 halves. 8 it would be the same as a 16 halves, right? Think of this as 8 over 1, so you double the top and bottom. And so we got y equals negative 23 halves is the y. And so putting these two answers together, if you like, you can restate it as the coordinates of a point, because that's really what this represents. That's the point where the two lines cross. Or if you want, you can just circle each separately. I don't particularly care. No, it does not. Okay, start over. All right, so here's an example that's a little bit different. It's got fractions in it, so we'll get a nice chance to practice our fractions here. Probably a good thing. So both of these equations are begging us, y equals stuff, x equals stuff. I think what I'll do is I'll take this x equals 3y plus 1/8 and I will replace it for that x in the first equation. The second equation says x is the same thing as 3y plus 1/8. So where I see x, I'll just put the 3y plus 1/8. So the top equation is now looking like this. Y equals negative 2/5. Multiplying. I got a 3y plus a 1/8. Okay, and then minus my 3/5. Okay, it looks a little long, but we can do this. First thing you got to do is you got to distribute this times this. Remember, the 3 is like a 3 over 1, and to multiply fractions, you just go straight across. So I'm getting a negative 6 over 5y And then here, if I don't cross cancel, I'm just going to go straight across, and it's going to look like a 2 over 40, which I will reduce in a minute, and then minus the 3/5. Okay, what should we do here? Well, we should definitely add 6/5 y on both sides. So 6/5 y is adding 1 y, but 1 y is the same as 5/5 y. And so this is going to give me 11/5 y. Okay, and then over here, those are canceling. Over here, I'm going to call that a negative 1/10 if you don't, or 1/20th, right? Just canceling 2 into 2 and 40 gives me 1 over 20. And then, since I would want this to also be over 20, I'm going to have to do the old times 4 over 4 trick, which gives me a minus 12 over 20. This is kind of fractiony. Okay, so 11/5 y equals, this will be a negative 13 over 20. And now, in order to finish solving for y, I should multiply both sides by the reciprocal. And I'm getting y equals negative 65. 20 times 11 would be what, 220? Oh, wait, I should cross cancel. What am I doing? What am I doing? Cross cancel. 5 goes into 5 once, 5 goes into 20 4 times. That's better. So I got a negative 13 over a 44. That's my solution for y. Now don't forget, you got to get x too. So let's get x in a nice pretty color. Come over here someplace. The bottom equation says x equals, so I go x equals 3 times the y, but the y is a negative 13 over 44, plus the 1/8. Okay, a little more fraction action. This is good. You should do a couple fractions before breakfast every day. So 3 times this will be a negative 39 over 44. Again, remember that's like a 3 over 1, so it's 1 times 44. Plus, well, it's hard to make 8 into 44. I'm going to have to use a bigger common denominator. I'm going to have to double the negative 39 to get a negative, what is that, 78 over 88. So that way I can multiply top and bottom over here by 11 and get 11 over 88. And so for my answer for x, negative 78 plus 11, negative what, 67? Oops, not 2 negatives. Negative 67 over 88. So there's your x, there's your y. Well, that was some good fraction practice, right? Don't leave home without fractions. Fractions are good for you. Okay. So on the last page, I got systems where something's going to go wrong. Now, you remember when we were graphing, sometimes we got the same line, sometimes we got parallel lines, so we'd say no solution because they never crossed. Well, what does that look like when you're solving algebraically? When you're solving by graphing, you can tell just by looking at it, hey, those are the same line. But when you're solving algebraically, what's going to happen? Let's just find out. So the first thing I'm going to do, again, this one's begging us. Take my negative 3/2 x and plug it into y on the first equation. 3x plus 2 times y, but y is negative 3/2 x plus 1. Okay, that equals a 4. Here we go. Let's simplify. 3x. If you multiply, think of this as 2 over 1. If you multiply 2 over 1 times 3 over 2, the 2's will cancel. You will get a negative 3x again. What, you don't trust me? Let's do it this way. See, the 2's cancel. You get a 3 over 1, negative. So that's that. 2 times 1 is a 2, of course, equals 4. And then here's the thing. 3x minus 3x. Now it's funny sometimes. Sometimes I see people say, what? I don't want to lose my x. I don't want to lose my x. And so they'll just put an x there. Well, 3x minus 3x is not x. 3x minus x is nothing, right? It's 0. It's not there anymore. There's no x. So your equation just looks like this. 2 equals 4, which should have you saying, wait a minute, what? I didn't think 2 equals 4. Is that a new thing? I don't remember that from anywhere. 2 equals 4? No, actually this is impossible, right? So I like to use the word impossible result. 2 equals 4 is an impossible result. And that helps me to remember that this is going to be no solution. These are actually parallel lines. Because you're trying to find a point that solves both equations. You're trying to find a point where the two lines would intersect, right? You're trying to find a, let's make the lines a little crooked. You're trying to find a point where they cross. You're trying to find a point that satisfies both equations. You're doing some legal stuff, you get to an impossible result. That means it's impossible to find a point where they cross. They are parallel. And I think as an exercise, you should probably bang out a quick graph of those lines and say, oh, they're parallel. So if you have an impossible result, this is worth highlighting. If you have an impossible result, you get no solution because they are parallel. Well, what's it look like if you get, the next case, of course, is going to be same line. Well, what's that look like? How do you get same line? Well, this is how you get same line. So I'm going to take this y equals stuff, plug it into the top one, 2x minus, shove this y in, which is 2x minus 5, equals 5. So 2x, distribute, I got minus 2x, I got plus 5, equals 5. Once more, 2x minus 2x, you could write 0x if you really wanted to, but really it's just 0, or you could just say it's not there, right? It's just not there. So 0 plus 5 is equal to 5. 5 equals 5. Now that's kind of a question mark, but it's a different kind of question mark, right? It's not that it's impossible. It's not, oh, this is an impossible result. This is an, but of course. I don't know. I think I want to say automatically true. That sounds better. Automatically true. Automatically solved, automatically true. Maybe true is a better word. Automatically true. In logic class, you would call this a tautology. This is because they are the same line. Oops. They are the same line, which is the answer I really like. They are the same line. They're on top of each other. You get a tautology, you get something that's automatically true. Why? Because for any point on one line, it's automatically a point on the other line. Everywhere up and down one line is the same as everywhere up and down the other line. So no matter what point you're talking about on the one line, it's on the other line too. The equation is automatically true, or when you combine them, it's automatically going to be true. So when you get this, a tautology, it's the same line. When you get this, which by the way, the official word I guess would be contradiction. When you get a contradiction, it would be no solution. So try to keep those two cases separate in your mind. If you get an impossible result, it's impossible to find a crossing point. They do not cross, they're parallel, no solution. If it's automatically true, it means it's easy to find a point where they cross. Any point on one line crosses the other one. It's automatic, it's there, it's going to happen. Okay, well that's a pretty good whirlwind introduction, I think, to the how to solve by substitution. And with that, I remind you to go get the problem set, posted in the, well, if you've printed this out, you've already seen where it is. It's posted in the course description, in the video description. And yeah, see you online, I guess. How do you turn this thing off?